So it's a 13.8. You want to find the relative maximum, relative minimum, okay? So we're just reviewing really calculus 1. So it's going to be extremes or extrema of the functions of several variables. Functions of several variables. So since your function is a real value function, so it makes sense to compare the value of the function. So that's why we talk about the maximum value and the minimum value of a function. So we define relative max, relative min, as we did before. So suppose we have a function, okay, let z equal to the, we focus on the function of two variables, of course. Z equal to the f of x, y, be defined. Okay, defined on the, on its domain, the domain D, and we pick D in R2, of course. And we select a point, okay, we define on the domain D in R2 containing a candidate for the maximum and the minimum point, containing the point x0, y0. I'm going to define relative max and the relative min. Okay, the largest value of function for a while, local or relative, and the largest value forever is going to be absolute max, then we get absolute min. Okay, so the first one. I go with the relative minimum first. F has a relative minimum, okay, minimum value at this point at x0, y0, if this is going to be a smallest value of the function just for one region. If f of, remember they are numbers, so we can talk about it. F of x0, y0 is going to be less than or equal to the f of x, y, just in a neighborhood of x0, y0. So it's going to be for all points x comma y, we say near x0, y0. So near means a near distance. Remember the neighborhood in this domain, if you like. We mean this is going to be like kind of a circle, if you like, and this is going to be the point x0, y0. Okay, when we say neighborhood, we mean a neighborhood of any point inside. Okay, any point inside this ball, we call it. Okay, because it can be defined for not R2, R3, or Rn. So these are going to be the point. Okay, it's a local minimum. Okay, and of course, if it's going to be the largest value of the function, then it's going to be absolute minimum. So f of x0, y0 is the absolute. Okay, absolute minimum of f if this is the smallest possible value of the function. So it's going to be f of x0, y0 is less than or equal to the f of xy forever. It's going to be for all x comma y in the domain of the function. Okay, so the as usual definition. So that's a local minimum. If you reverse these inequalities, then you get the local, okay, local maximum. So similarly, we can say that the f has, okay, f has a relative, just repeat that expression. Relative maximum value at the point x0, y0, if the condition is going to be no, the inequality is going to be reversed. if f of x0, y0 is greater than or equal to the f of xy in the neighborhood of x0, y0. So for all points x comma y near in a neighborhood near x0, y0. And it's going to be absolute. Okay, f of x0, y0 is the absolute. Okay, absolute maximum if this is the largest value of the function. So it's going to be greater than or equal to the f of x, y for all x, y in the domain of the function. So as you can see, it's just usual definition would satisfy because the range of the function are numbers, is the real valued function. So we set up the definition. Next, the position to find them. You know that we did have a theorem for the function of one variable. And in order to get the relative max, relative mean, we focus on two different positions. The position that you have horizontal tangent line and the position that you have vertical tangent line. When we get the horizontal tangent line, the derivative of the function would be 0. And when we get the vertical tangent line, this is the case that the derivative of function does not exist. So we did have a theorem, we call it the Fermat theorem, that if you have a relative max on the mean, would satisfy these two conditions, but not in general. That's why these numbers refer to them as critical numbers, and they are going to be the candidate for the maximum or a minimum. So we are going to bring them back, and we call them critical numbers over here, but we call them critical points here to get these numbers to, okay? So we're just modifying what we know from the past. So we are going to get critical points this time. What is critical? Okay, critical points. Or sometimes in this course, or even in Calculus 1, we call it a stationary points. So all of them are going to be the same. But we stay with the critical points. That's it. So these are going to be the one I talk about it. You get horizontal tangent line and the vertical tangent line that you have to modify it here. And what is going to be those cases? So on the function of one variable, the condition would be f prime equal to 0. F prime does not exist. On a function of several variables, you replace the f prime by the partial derivatives. Okay, so this is how we're going to extend those definitions. So there you are. So we have a function again. Suppose z equal to the f of x, y again is going to be defined on the domain D, and x0, y0 is in D. Okay, now I want to define critical values. So two cases. So there you are. So this point x0, y0 is going to be called a critical point, critical point of f or for f if now one of these conditions satisfy, like the one that we did for function one variable. If one of the, or either one of the following is true. Again, in case of one variable, f prime 0 horizontal tangent line, f prime does not exist vertical. So we change them into the partial derivative. So the first condition would be the partial derivative respect to the x at x0, y0 this must be 0. And at the same time, the partial derivative with respect to the y of x0, y0 must be 0. Remember, it must satisfy both of them. So in order to find that, we check these two, we write it down as a system of two equations with two variables, and we find it. In calculus 1, we have f prime equal to 0. The second case, that idea of the vertical tangent line or derivative does not exist, the partial derivative does not exist. So it's going to be f partial derivative with respect to the x, okay, or partial derivative with respect to the y does not exist. Okay, so again, we copy what we have for the, okay, we copy what we have for the function of, okay, function of one variable, but you check it, change it to the partial fraction, partial derivative. Any question? So we set up nicely, we bring the tools, the candidates. Okay, then we continue. How about the Fermat theorem? Remember, the Fermat theorem will tell you that if you have a relative maximum, then it would satisfy these conditions. Okay, if you have a relative at the, is a function of one variable. At C, you have a relative maximum to minimum. Remember, there are two possibilities: f prime of C equal to 0, f prime of C does not exist. So that the result was the one that we call it critical value. Same thing. So we are going to change it into this language. So same Fermat theorem. So that is the key theorem over there. It's going to be the same thing here. So Fermat, great, you know, French mathematicians, Fermat's theorem. Same thing. If you have if you know that it's a relative extremum, then you must get that it's going to be critical values. There you are. If z equal to the f of x comma y has a relative, okay, relative extremum, means a maximum or a minimum at x0, y0 in D. Remember, the result was f prime of C equal to the 0, f prime of C does not exist. Right? In the language that we have over here, this simply means this is a critical point. So if it has a relative extrema at this point, then x0, y0 is a critical point. So that's about. You know that in the case of the function of one variable, we prove this theorem first, then we call it critical value. Okay, and it would be easy to prove, like the one that you proved for these functions. For the, if you remember from calculus 1, we just write the definition of the derivative and we just check it. We use the right left limits to prove that the derivative is equal to 0. It's the same thing. Can be done here. That we don't prove it. It's exactly the same one. Okay, so that gives us an idea. So if you have a relative maximum minimum, then it's going to be a critical point. You know that from function of one variable, the converse is not true, which means if you find the derivative of the function and you let it equal to 0, don't expect to have that point to be a maximum or minimum. Remember in calculus 1, the example was f of x equal to the x cubed. It's the same thing over here. So remind yourself that the converse of this theorem is not true. Same thing, doesn't matter. Okay, so remind ourselves that, note that this means if you have a critical point, doesn't mean that you get a maximum. You have to test it. Note that the converse of the theorem, okay, converse of the Fermat theorem is not true in general. Is not true. Okay, not true in general. So this means I do have a function and I do have a point for which, that the derivative is 0, but the point is not going to be max on the minimum. If you like example, in calculus 1, the example is x cubed. But for this one, you see, for example, something similar. For example, consider, it's nice to know, okay, consider the function to see when you want to extend. So you have to be careful. You cannot reject whatever you did for the function of one variable. So consider this function, f of x y equal to the y squared minus x squared. See this function? It's a polynomial, it's a nice one. So you may find the derivative, in this case, partial derivative, let it equal to 0, and expect to get the max and the minimum. So let's find out. You see the partial derivative with respect to the x in function of one variable derivative, in a function of several variable partial derivatives. That will be negative 2x. Okay, derivative respect to the y, 2y. So we will let them equal to the 0. So if we let f of x equal to the 0, at the same time here, f of y equal to the 0. So we have this system of the equation, negative 2x equal to the 0, and 2y equal to the 0. So that gives 0, 0. X equal to the 0, y equal to the 0. So you have a 0, 0. You see, this is a critical point because it's satisfied. You see, you should let derivative equal to the 0. This is going to be critical point first. The candidate for the max and the min is a critical point. But we can show that this point is not the maximum or the minimum. But f of 0, 0, if you go to the function, remember it's a y squared, it's a 0 squared minus 0 squared, which is 0. So is not going to be, is neither okay, a relative minimum, okay, or nor, a relative, or nor a relative maximum. You see, it's the same thing. You can't have it. You can prove it, of course. To prove it is, it's nice to know. If somebody said it's a minimum, so this means this must be lowest minimum that we have. Look at this one. Nice to know. Note that if you say it's minimum, I give you this one. What is f of x and 0? Remember, your function is y squared minus x squared. So I fix the y 0 minus x squared. So that gives me negative x squared, which is always negative. So this means f of x 0 is less than f of 0, 0. So this means f of 0, 0 is not a relative minimum because I have something which is less than this. Okay, so f of 0, 0 is not a relative minimum. Okay, because I give you many points. You can replace x by anything you like. So I have quite a lot of numbers. Also, if you say it's a maximum, I give you this one. How about f of 0 and y? So that gives y squared minus 0, which is y squared. And the y squared is positive, but this is f of 0, 0. So I have f of 0 and y, which is bigger than f of 0, 0. So I have something for you, many values. that are going to be greater than f of 0, 0. So f of 0, 0 is not a relative. Is not a relative maximum. Okay? So the same problem that we did have for the function of one variable, we have it over here. So this means critical points are just the candidate for the maximum and the minimum. So this means you need to test it. Okay, you find these critical points or the critical points, but you test them. In this case, we have a name for it. We are going to see it. If, in this case, 0, 0 is called a saddle point. Saddle point means it is a, sometimes they call it a stationary point, but saddle point is the one that we use in this book. So it's a critical number. It's a critical point, but it's not the maximum and the minimum. We call it a saddle point. So this means the need for a test. Okay, so we have the candidate, but we have to test it. In calculus 1, function of one variable, you have the first derivative test and the second derivative test. In the function of several variables, the second derivative test is a version, of course, of the second derivative test is much easier to handle. So that's why we are going to take that one. It doesn't mean that you cannot form a kind of the first derivative test. You can do that. I gave a couple of honors program, okay, project to the students of this. When I take this one in person, there are a number of the articles. Those they try to form something from the directional derivative, not these type of derivatives. Okay, but we just stay with your book. We just go with the second derivative test, which is very popular and easy to apply. And this is going to be your job for the coming, one problem on the test. Okay, any question? So we build up to see how you generalize, okay, get a feeling when you go from one-dimensional to the two-dimensional, three-dimensional, we have to repair something in between, but we'll be able to do it at the end. So we find these critical points first. You solve that system of the equation, f sub x equal to 0, f sub y equal to 0. Then you test it. How are you going to test it? A kind of second derivative test, okay? So this is your main job. You should be careful about the algebra of solving that system of the equation. Otherwise, you usually have to no worry, okay? So this is the only test that you're going to use. The second derivative. Second derivative test. Okay, we refer to it as a second derivative test as in calculus 1. That's it. Remember, in calculus 1, second derivative test use concavity. So you find the second derivative, you drop the number, okay, the C, the critical value in it. If the second derivative is positive, you say it's concave up. So we get the minimum. If the second derivative is negative, you say it's concave down. Then you say you have a maximum. But we don't have the derivative. We are going to adjust it with the partial derivatives. Okay, so this is going to be a kind of adjustment that we're going to do. Okay, so what is this? So suppose you have a function. Here you are. So suppose you have a function and you already find the critical numbers, critical points. Suppose that the function, okay, we have a function, the given function. The function f has continuous, you need partial derivatives, are continuous partial, has continuous partial derivatives, continuous partial derivatives on its domain, on its domain D and containing a point, okay, containing as usual, containing the point, the fixed point that you find it already, x0, y0, for which, okay, for which this is the result of the, okay, as in calculus 1. You can only use it if the critical numbers are coming from the type 1, coming from where they get horizontal tangent line, f prime equal to 0. It's the same for this one. But it's coming from the, of course, this, the partial derivative to be 0. So f sub x at x0, y0 is equal to the 0. And at the same time, f sub y x0, y0 going to be equal to 0. So this means you already solved this system of the equation and you find this point. If this does not exist, of course, you cannot use this test. So we find the candidate, now we want to test it. This is how we're going to test it. To test. Okay, to test for relative maximum and minimum, or relative extremum. Okay, extremum of the function. We have the following of the function f. We have a kind of second derivative of the code. We are going to consider this quantity, if you like. Consider the quantity. The quantity that we're going to consider, depends. The different people use different notation. So we go with the lowercase d. We can go with the d in uppercase, doesn't matter. Is the determinant of a matrix. Got it, d. It's going to be this. You see, it's going to be f of xx at x0, y0 times it by f of y at x0, y0 minus derivative of fxy at x0, y0 all squared. That's a d. So in short, this is the way we write it down. We say that d is equal to f11 times by f22 minus f12 squared. That's 1. We will see this again in the next chapter. We call it Jacobian later on, but not now. So if you want to see what's going to be the origin, this is the origin that you see in the next chapter. D is in fact the determinant of this matrix. So it's going to be the partial derivatives. With the first row is going to be f11, it's going to be f12, then we get f21 and f22. You see, it's going to be a matrix, 2 by 2 matrix, and you just cross multiply the determinant. It's going to be f11, f22 minus, okay, it's going to be minus f12 times f21. But you know that these two are the same because you assume that the partial derivatives are continuous. So that's why we say f11, f22 minus f12 squared. It's going to be the same as if you go with the, okay, f12, f21, both of them are going to be the same. Okay, it's a famous determinant, and you'll see it again. So it's a function of 2 variables. You can do it for 3 variables too. Okay, so what you do is you already got your critical points. You have to form the D for us, and then consider the following. Remember, in the case of function of 1 variable, if the second derivative is positive, concave up a minimum, second derivative negative, then we get concave down, we get the maximum. But the situation here is going to be these 3 cases. Case 1. The case 1 is if D is positive. Jacobian, if D is positive, remember at point, it's going to be number. If it's positive and fxx or fyy, it doesn't matter. This is also positive. Okay, if this is going to be positive, you look at the second derivative. Second derivative positive, concave up, we get the minimum. Okay, if it's going to be a kind of, up, we get the minimum. So if this is going to be the case, then F has a relative minimum. Relative minimum. Okay, relative minimum at x0, y0. So make sure you have this formula. You can add it to your collection and make sure you get this one. Okay, so if this is positive, you check fxx and fyy, both of them are the same. If it's going to be positive, it's a minimum because it's going to be curving up. And the other part is if it's going to be negative. So the case 2 is that if D again stay positive, and then fxx at x0, y0 happen to be negative, so the negative would be kind of concave down if you like. So we get a maximum as in calculus 1. If this is going to be the case, f has a relative, okay, relative maximum at x0, y0. You know that you have to find f of x0, y0 as a value. So this is going to be the case. The other cases are going to be the bad one. Case 3, if D is going to be negative, we don't have anything to talk about it. If D is going to be negative, we can say only this point is not a maximum, the minimum. So it's a saddle point. Then the point x0, y0, z0 is a saddle point, You know that for this is x0, y0, f of x0 and y0. So this is going to be a saddle point. Okay, so if it's going to be positive, it's going to be the good one. If it's going to be negative, you just stop and it's a saddle point. And the case 4, if this is going to be 0, it's like the second derivative test of function of one variable. We don't have anything to say. The test fails. So if this is going to be 0, the test fails. We cannot use this test. Then the test, okay, is fails. So we can find other method to check it. So this is going to be the second derivative test and your job. Your one function and you test it for us. Okay, kind of application or the version from the function of one variable to the second variable. Okay, and there are many others, that if you are going to be interested in researching these type of ideas, and there are some others, but they are not nice. This is a very nice version, okay, of the best that you can have. Okay, so your job is the first part, really. Make sure you solve this equation all right. So I give you a list and I have posted all the solutions. Just check them because some of those equations need to be practiced in advance. Just make sure you're familiar with algebra. Otherwise, straightforward. Okay, so one of those 11 questions that you have on the test is this one. Okay, are you ready? Let's do it. Find the relative extrema. Find the relative, very much like calculus 1. Relative extrema of this function. The function is f of x comma y is equal to the negative x cubed plus 4xy, okay, minus 2y squared plus 1. That's it. So as a function of one variable, you find the critical points first. To find the critical value, derivative equal to the 0, but derivative would be partial derivatives. Then you form the D, the Jacobian, and check it. Okay, are you ready? Solution, go for it. It's a polynomial type, so the domain is everything, nothing to worry about. R2, that's the domain. So you have to find the critical, you see. The first step is find Find the critical points. Critical points. That's instruction by solving the system. Solving the system. The system that you have to solve is this one. Partial derivative with respect to the x equal to the 0 and the partial derivative with respect to the y equal to. That's your first job or the main job. Carefully find the partials and bring it here. Partials respect to the x. Differentiate negative 3x squared 4y negative 3x squared. Okay, and the plus 4y. This is it. F sub y respect to y. This is 0. That's a 4x, and this is negative 4y. So that gives a 4x minus 4y. That's it. Put them into a system of the equation and solve, addition method, substitution method. These are the various methods that we use. So it's going to be negative 3x squared plus 4y equal to the 0. And we have the 4x minus 4y equal to the 0. That's it. To solve this system, you check addition method or substitution. Addition is easier here because the 4y and the 4y would cancel out and you get the x and you'll be able to do it. Otherwise, substitution method, okay? So addition method is easier. So you bring this down. So that gives it negative 3x squared plus 4x equal to the 0. So we solve this one. So just factor out the x. So x out, that gives me negative 3x plus 4 equal to the 0. So you have two solutions. So the solutions are going to be x equal to the 0 is one of them. And you let this one to be 0, so the other one would be x equal to the 4/3. So that's going to be your x. You go back, substitute x in one of these equations to get the y. That would be the next step. Okay, x equal to the 0, I just choose this one. So x equal to the 0, I substitute. Just want to show you that I put it here. So 4 times 0 minus 4y equal to the 0. So that give me, okay, y equal to 0 too, because everything would be 0. Okay, so that's it. It's going to be negative 4y equal to 0, so y 0. So I have 1 point. So the first point that I'm going to check is I have the x and the y equal to the 0, 0. This is one candidate, 0, 0. You can call it A, B, whatever you like. That is going to be the first point. Okay, any question? Check the 4/3. So x equal to the 4/3. So again, I put it here. Going to be 4 times x, 4 times 4/3 minus 4y equal to the 0. Okay, we can solve this one. You can drop the 4s. So that gives you 4/3 minus y equal to the 0. So y would be 4/3. So you have the second point. So the point x, y is going to be 4/3 and 4/3. That's it. So you have two critical points to check. Okay, so critical points. Critical points. Okay, you can carry on as is, or you can label it. For example, I label A as a 0, 0, and I label the B as 4/3 and 4/3. Okay, that's going to be your first step. Any question? Now we have to test it. You have to do each point separately, okay? So you have to form the D first, Jacobian. Okay, and check the D. If D is going to be negative, it's out. It's going to be positive, we continue. Okay, are you done? So testing, second derivative test. That's it. So testing part. Testing. We have only one test, of course. Okay, so the test is a second derivative test. So you better find the D first. Okay, we go with the D first. D F11 F22 minus F12 squared. So bring this first. F1, you already got the F1. F1 was a negative 3x squared, okay, plus 4y. That's the F1. Differentiate it again to get the F11, so that give a F11. Respect to the x, that give a negative 6x. That's F1. Then the F2. Okay, F2, you did have it 4x minus 4y. So we are going to make it F22. That's going to be F22. Differentiate again respect to the y, that gives a negative 4. And you need F12. This is F1, differentiate respect to the y. So that gives you F12, which is equal to 4. Okay. Now we're going to form the D for each one of them separately. Okay. So what I'm going to do, the first point, I'm going to pick the A. Okay. You just do it one by one, you can call it A or whatever you like. So the first point is 0, 0. So I'm going to check these at 0, 0. Okay. So if you put the 0, 0 here, so F1 would be, I'm sorry, what I want, F11. This F11, so F11 would be 0. F11 would be 0. F22, F22 would be in negative 4. And the F12 is 4. F12 is 4. So I can find the D here. So the D for this point is going to be equal to, that's it. F11 times, just write it down, you know what's going on. This is it. Minus F12 squared is going to be minus 4 squared. So that gives me 0 minus 16, which is equal to the negative 16. So negative 16, which is okay, which is bad, because that tells you that this point is going to be a saddle point. Okay, so this means, so the point that you have, you see 0, 0, and f of 0, 0. 0, 0, f of 0, 0, if you go to the function substitute, that give you 1. So 0, 0, 1 is a saddle point. Is a saddle point. Any question? Remember, f of 0, 0, you go back to the function. You see that's function. If you put x equal to the 0, y equal to the 0 over here, so f of 0, 0 would be 1. Because you have to denote it as a point in a space in this case. Okay, so that we are done with the first one, the first point. Any question? And you have one more point to do. So go with the second one. Repeat it again. So the second point was 4/3 and 4/3. You have to do the same thing. Okay, we have to find you have the F11. Okay, you go to the F11, and this is F11. F11 was a negative 6. You substitute. So I just show you that this was a negative 6x, so it's going to be negative 6 times the 4/3. Okay, so that gives you 24/3, which is going to be -8. So that would be F11, -8. Okay, F22 is still that -4. So F22 is a -4. And we have to find the F12. F12 is also 4. So F12 is equal to 4. There's no X and the Y on those. Okay, question? So find the D for this one. So the D is F11, F22 minus F12 squared. So the F11 is a -8 times F22 is a -4 minus F12 squared, 4 squared. So that gives you 32 minus 16. Okay, 32 minus 16 is bigger than 0. Okay, it's going to be equal to the 16, which is bigger than 0. So D would be positive. Okay, as soon as we get the D positive, so we're going to compare it with the F11. Okay, D is positive and F11 at this point is a -8. Okay, D positive, F11 is equal to the -8, which is a negative. Remember, it's like negative would be concave done, if you like. Done. We have a maximum. Okay, that gives you an idea. So this means f of, okay, so this means f of 4/3 and the 4/3. Remember, the value of the function is the one we are going to consider. This is going to be a relative maximum, but you have to find it. Give us the value because this is the maximum value that we are interested in. Okay, any question? So as soon as the D is positive, you can check F11 or F22, both of them could be the same thing. But you have to find this one. You go to the function, substitute carefully and get the result. So this is it, f of 4/3 and the 4/3 into the function. The function was a -x cubed. So it's going to be -4/3 cubed. Okay, I just substitute plus 4xy plus 4. Okay, that's a 4/3 and the 4/3. Okay. And minus 2y squared is going to be -2 times 4/3 squared plus 1. Okay, just do the original function and just substitute, simplify. It's not difficult. So that gives me -64/27. And this would be 16, 64 again, 64/9. Okay, and that would be minus 4 squared would be 16. 16 times 2 would be 32. So minus 32. And that's a 3 squared and a plus 1. A little bit of simplification, these two first. So that gives a -64/27. You can use your calculator if you like. This would be 32/9 plus 1. And just a common denominator give you the final answer. Okay, find the common denominator would be 27 and just put those numbers together. Okay, that would be 27, so -64, and that give you 96 and the 27. So the final answer is 59/27. Okay, so this means f of, sorry, right on here, f of 4/3 and the 4/3, which is equal to the 59/27, is a relative. Okay, it's going to be relative maximum value of your function. Okay, get the, keep the procedure, and it's usually a nice problem. There is a couple of tricky one when you want to solve that first equation, f sub x, f sub y, just check it. That you may have to use the substitution method, but the one that you're going to have is going to be straightforward, but check the one that you have on the practice test. Especially check the first part to make sure that you are able to go through that system of the equations. But otherwise, nothing to worry about. Okay, so you can see this is going to be the best option for the relative maximum rate minimum, and then you can continue like in calculus 1. Okay, get the kind of application problems, it depends which discipline are going to be. Okay, if you are going to be doing business, physics, etc. So we are not going to get through those type of applications. You can read it for yourself. That is the idea of the next 13.9. Sometimes we do a couple of, they are mostly talk about cost function, revenue function. It's not a big deal really. You can read it for yourself. But any question? Now we do only one type of the application problems for you. That would be quite interesting. We just stay in course on the course that you see. Nicely, we extend whatever we learn in calculus 1. There is one more, which is more interesting. A version of the problem in calculus 1. And we are going to do it again here. This group is popular. There are you can use it, your calculator, and do it. But mathematically, it's interesting. That's why I'm going to give you a special case of this to finish this chapter. Okay, any question on this one? So one problem of those 11 are going to be this one. And one more problem that we extend from calculus 1, it's quite interesting. So 13.9, you read it for yourself. We are not going to get, this is optimization problem. Just finding the maximum minimum. You're not going to do a question on this one, and you are not going to lose anything here, of course. But the next one is 13.10. So we are going to get point 10. Remember, we have a kind of easy problem. The Fermat problem in calculus 1 is that they usually give you what? They say find two numbers. Find two possible numbers whose sum is 100 and the product is a maximum. That's a problem that we do in algebra, and then we can do it in calculus. So the way we do this type of problems, we form a function in calculus 1. We form a function that satisfies these two conditions, and then we maximize the function using the derivative of the function. But in the case of the function of 2 variables and 3 variables, you can do the same thing. But the thing's getting more complicated. You can use those methods. There is a nice method, if you like, to do these type of ideas. Mathematically, it's nice, but sometimes it's boring. It takes time to do it. When, of course, we have a function of 3 variables, 4 variables, etc. So what I'm going to do, I'm going to explain this method for you for function of 2 variables. And we would like to question you on this on the test because it's a great argument. Okay, so that's the idea of 39. We call it Lagrange multipliers, the method. Lagrange, great French mathematician. Lagrange multipliers. That's it. Of course, Lagrange is one of those people who's responsible for the definition of the derivative of the function and notation that we use. I think f prime of x is due to the Lagrange. Okay, what is his method? So what I'm going to do, I give you one example from calculus 1 or algebra, and together we extend it to a formula that's going to be Lagrange multiplier. Otherwise, you are not going to be understanding or following me what's going on with this method. Okay, so let's review first, then we change it to a nice formula, and then one example, and we're done. Okay, let's review first that famous Fermat problem in calculus 1. or in algebra. What's a review? The review is this problem. Find two positive numbers. Find two positive numbers. Two positive numbers. Numbers whose sum is 100 and whose product is a maximum. You know that the history about this problem is quite interesting. It's happened first in the Greek literature. And the way they use it is instead of sum of the numbers, they were interested in what? They were interested in they consider a rectangle. The product is going to be the area of the rectangle and the sum would be the perimeter of a rectangle. So the original problem was you would like to find the dimension of a rectangle. Dimension with a rectangle whose perimeter is 100 and whose area is the largest. Okay, so that's the original problem. We search on internet. The original problem is quite nice, it's geometry. But Fermat was the one that took this problem and he just used the derivative indirectly to solve the problem. And later on, the people find out that, he just created the definition of the derivative of the function. So that's why this problem would have a long history. Now, let's say we're going to do it in calculus 1. So what we do, solution, then we extend it into the version of the three-dimensional. So what we do, we change it to the symbolic form. Symbolic form is what? Find two positive numbers. So we say that suppose x and y are two positive numbers, two positive numbers with this condition such that the sum x plus y is equal to 100 and xy is a maximum. You see that's going to run. So this basically means that you want to maximize the xy with the condition that, with the given condition that x plus y is equal to the 100, or with the restriction, constraint restriction. So the way we do it in calculus 1, this quantity, we call it a function. Okay, the quantity that you want to minimize or maximize, you call it a function. Suppose f of x equal to the x times y. But since we work only with function of one variable, we use the condition, we change it to say, but x plus y is equal to the 100. So I'm going to find the y, which is 100 minus x. Then I bring it back here. So my function f of x equal to the x times y would be changed into the x times 100 minus x. Now this function is of course easy to handle, 100x minus x squared. So I differentiate the function to find the critical values, which is going to be 100 minus 2x. Okay, I did it equal to the 0. So that give me 2x equal to the 100 and x equal to the 50 as a critical point. Okay, then of course I have to test it. I test it with the second derivative test. So that give me -2, which is less than 0. So less than 0 means concave done. So I guarantee that I have a maximum. So f has a maximum, has a max at x equal to the 50. Okay, so I can find the y. So y was 100 minus x, which is going to be 100 minus 50, which is equal to the 50. So x equal to the y. X equal to the y equal to the 50 is going to be the solution. Okay. And you know that this is the result is from geometry point of view, we say among all the rectangles, with a fixed perimeter, the one with the largest area is a square. That's the result of the geometry among all the rectangles with the fixed perimeter, this 100 that we got over here, or 200 in that case. Okay, one with the largest area is going to be, okay, a square. Okay, this is calculus 1 version. So now calculus 2 or calculus 3. You see the difficulty in calculus 1 is this is, we say f of x, but you have x and y. So now what we can do is we can change it to the function of two variables, okay? So let's see, what can you do? How are we going to make a new formula for us? So calculus 3 version. Cal 3 version. This would be the beginning of the Lagrange multiplier. So what we can do is instead of f of x, we can call this one f of x comma y, which is going to be x times y. Okay, this is going to be the function. So now what do you want? You want to maximize this one, but you have a given condition. So the question now is going to be, you see the question is going to be maximize. Okay, maximize the function f of x comma y, which is equal to the xy, under the condition, under the given condition, or the expression are going to be constraint. It's the same thing. Okay, maximize f of x, y, xy under the condition that what? X plus y is equal to the x plus y is equal to the 100. You see, this is going to be the version in three-dimensional, if you like, or in calculus 3 version. So if you find that maximum point, you should satisfy these two conditions at the same time. Satisfy the first one and satisfy the second one. So what we are going to do, we already got this function. We move the 100 to the other side and we introduce that one as a new function. Okay. So what we do is we get this function f of xy equal to the x times y. This is the given function. We introduce the second function, xy equal to the x plus y minus 100. You see? So what we would like to do is we would like to get a, okay, you would like to get a common solution of these two really. So if you just think about it, what would be the condition that you are going to have for those numbers? So I'm going to go to the next page to explain it, and I get an excuse to like it. So what you would like really to do is you have to find a point x0, y0 that satisfies these two conditions. That's all you have to do. So if you see, if the solution, if that point that you're really looking for, if the solution, okay, if the solution is a point like x0, y0, then x0, y0 is what? Is going to be, is on the graph, of both functions, Okay, because this is going to be a common solution they're going to have. You see, look at this one. Suppose this is the graph of one function, and this is going to be the graph of other function. You see, so this is going to be the point x0, y0 that you're going to have. Okay, now look at this one. This is going to be the intersection point of these two. Now, if you consider the tangent line at this point for both graph, okay, it's going to be the tangent line. And this is going to be the tangent line at this point. So what is going to be the normal line? So what's going to be a relationship between the normal line of these two, these two graphs? Remember, we already talked about it. We talked about it, the gradient, remember? The gradient of the function is going to be a normal vector. So in this case, this means, you see, if you get one of them to be, if you get the normal, you see, if you consider the normal to one of them, you see, if you consider the normal to one of them to be gradient of the G, for example, then it's going to be the same for the normal to the other one, which is going to be the gradient of the F. So basically, the conclusion of this argument informally means that the gradient of the F, if you like, the gradient of the F at the point x0, y0 is going to be kind of the same, or it's going to be parallel to the gradient of the G at x0 and y0. And you know that two lines are going to be parallel if one of them is going to be the multiply, okay, a scalar multiple of the other one. So this basically means the gradient of the F, if you like, x0, y0 is a scalar multiple of the gradient of the other one. You see? This would happen for all these type of function. This lambda that you find over here, okay, we call it lambda all the time, is a scalar. Lambda is called a Lagrange multiplier. Okay, Lagrange multiplier. So this means if this type of problem is given to you, you can form this inequality to relate them together. You relate them together, you find the lambda. If you find the lambda, then you go back and find the x0 and the y0, and that give you the job. And that was the interpretation. I give you a break, I come back, I make it official of how we're going to do it, and we give you one example, to be able to do that. This method is just informally, I tell you what it's going to be happen. So two functions would be given to you. One of them is going to be the function that you want to maximally minimize. The other function is going to be the constraint. The constraint mostly is going to be kind of a circle. Most of the time, ellipses are going to be the one. So you form this equality equation. You find the gradient of both sides. You let them equal to each other, and it's going to be just algebra. A system of the equation. You find the lambda and the x0, y0 from here. It's quite interesting one. Okay, it's 12 o'clock. Okay, let's have something like 10, 12 minutes. We come back. I give one example of this, and then we go over the practice test, and we're done. Okay, see you then. Okay, so let's make this one official. So a function would be given. Okay, you want to find the maximum and minimum of the function. Okay, maximum value, but under the given condition that we call it constraint. So we are going to use this fact that the gradient are going to be related to each other, and we find a relationship, and we'll be able to find it. Okay, so this theorem would be the the conclusion of those arguments, and this is called the method of the Lagrange multiplier. The result of it. So this is the result or the techniques that we're going to use to maximize or minimize those expressions, functions. So method of, okay, that's it, the Lagrange multiplier. Lagrange multipliers. So you are going to be having two functions. So let f and g be functions. Okay, be functions with continuous, of course, because you want to find the gradient, you must make sure that you have a continuous partial derivatives with continuous. Okay, continuous first order partial derivatives, enable us to find the gradient. Now, if a point, okay, let's say if f of x, y, the function, has the relative max or the mean, relative extremum at the given point, at a point. It's the point that you have to find, or you are looking to find. As a relative extremum at the point x0, y0, subject to, or under the condition, subject to the given condition. To the condition is going to be called constraint or condition. Okay, constraint that we noted by g of x comma y. That's the equation of the constraint. Okay, most is going to be ellipses, circles, etc. If this is going to be the case, and we talk about it, the gradient are going to be parallel, then the gradient of the function f at x0, y0, and the gradient of the function g, x0, y0, are parallel. Okay, so you know that if two lines are going to be parallel, one of them is a multiple of the other one, a scalar multiple of the other one. So if this is going to be the case, okay, then you are going to have, if the gradient of the g at x0, y0 is not equal to the 0, then there is a scalar. Okay, there is going to be the scalar that we call it lambda, such that you can use any number you like, but this is the usual notation. Such that, one line, one function, okay, that's it, or one vector is going to be a scalar multiple of the other one, the gradient. Okay, gradient of the f x0, y0 is going to be lambda times the gradient of the g at x0, y0. Lambda, as we talk about it, is called a Lagrange multiplier. Lagrange. Okay, it's going to be Lagrange. It's LA. Lagrange multiplier. That's it. It's exactly what I did for that example. So your job is two functions would be given to f of x and the y. The function f would be given. They ask for the relative maximum and minimum under the condition that those points which should satisfy, a given condition two. That condition, if whatever it is, it's going to be an equation. You move it to the other side. You call it g of xy. Then you are going to find the x0 and the y0. This is your job. X0 and y0. So you form this inequality. Then you have three variables unknown to find: x0, y0, and lambda. So that gives you three equations, a system of three equations, three variables. You can find it. Okay, sometimes it takes the times to find, but for the function of two variables, it's fine. And this is where we give you example, but I give you a hint for a function three variables as well. Okay, so a nice method. There's one question to know it. Of course, if you have a function of several variables, it can be done. It takes times, but there are some softwares that you can do it. Just apply it. So if you are going to be measuring something that you need numerical, analysis type problems, so that would be useful, and you must know the name. Okay, so the example, a typical example is this one. Let me give one of them, not complicated one. You just want to make sure that you remember this method. So that would be the idea. Okay, so find the maximum and the minimum. This is it. Find the maximum. Okay, maximum and minimum value of this function, of the function f of x comma y equal to x times y, that the product, subject to or under the condition, subject to the condition or to the constraint. The constraint is x squared plus 4y squared equal to 16. So you want your points are going to be on an ellipsis over here. Okay, an ellipse, x squared plus 4y squared to the 16, and at the same time would make the product to be a maximum. For some linear cases, if you already taken, when you take college algebra, sometimes we talk about it, but we use graphing to do these type of ideas over there. And it's quite interesting, interpretation of this. Okay, there you are. Now what you have to do, you have to form that Lagrange equation first, okay, and do the job. So first thing to do, you have to introduce a g function, your constraint function. You move the 16 to the other side, and you're going to call this one g function, okay? So this is it. You are going to suppose, so you have to suppose your g function to be, okay, g of x comma y is going to be equal to the x squared minus 4y squared minus 60. Remember, g of xy equal to the 0. That's your constraint. So we already talked about this story. We know what to do. So what you have to do is, we know that if there is going to be maximum minimum that should satisfy this condition. So we'd like to find a scalar. Find a scalar. We know that there is one according to the theorem. Find a scalar lambda such that this condition satisfies the gradient of the f x y to be equal to the lambda of the gradient of the gxy. When we talk about these gradients are going to be normal vectors, and in that common point, those normal vectors are going to be the same. They are parallel, so they should satisfy this condition. Okay, so there you are. So form these conditions. Okay, you know that the gradient of the f, remind you that the gradient of the f is going to be f sub x and f sub y. the partial derivatives. And in the case of the f function, the partial derivative with respect to the x would be y, and the partial derivative with respect to the y would be x. This is the file, okay? And on the other side, for the g function, the gradient of the g is just a g sub x. You can do it right away. Just explain it. And this is going to be gy. This is your g function. Find the partials. Partial respect to the x would be 2x. And the partial respect to the y would be minus or the negative 8y. Okay. So that would be 8. Where is the negative that I got? I made a mistake here. That is, it's x squared plus 4y squared. So that's positive. Okay, so that would be positive. So that will be positive 8y. Okay, now let them to be equal to each other. Okay, so we're going to form this identity over here. So that would give us, this is it. We end up with the yx to be equal to the lambda times the 2x 8y. Okay, the lambda, you know, this is scalar, just take it inside. So you are going to have the yx equal to the 2 lambda x and the 8 lambda y. And you know the two vectors are going to be equal to each other if the corresponding, coordinates are going to be the same. So these two must be the same and these two the same too. So that gives you a system of the equation. Remember, you are looking for the x, y, and the lambda. So from this part, you are going to get the y equal to the 2 lambda x. Okay, and from the other part is going to be x equal to the 8 lambda y. 8 lambda y. And then this is going to be two equations. You need the third one. The third one is the constraint, because whatever you have, it should be on this. Okay, so you add this part yourself. Okay, x squared plus 4y squared equal to 60. Any question? Now, this is the system that we have to solve. Remember, you are looking for the x and the y that satisfy this condition. So the way they solve it is a different way to do it. So we usually eliminate the lambda between these two. Then you are going to have one equation in terms of the x and the y, and there is another one here. So a system of two equations, two variables give us the result. Okay, so different way to look into it. And that's the usual practice. So the usual practice is going to be the case. From this one, you are going to find the lambda. So your lambda would be, okay, you divide by 2x, so that gives y equal to the 2x. Okay, and from this part, you get your lambda, again, is going to be x over 8y. Okay, the lambda. So that will help you to let these two be equal to each other. So that gives y equal to the 2x, and this is going to be x equal to the 8y. Okay. You can cross multiply. If you cross multiply, you see cross multiply. So that give you what? That give you 8. I stay here. That give you 8y squared equal to the 2x squared. And you simplify that, give you 4y squared equal to the x squared. So this is going to be the result of the first part all the time. So your system of the equation now is going to be reducing to equation of two variables. So you are going to get this x squared equal to the 4y squared, and then we get the x squared plus 4y squared equal to the 16. Okay, it's always the case. You have to find the lambda in both the first and the second, and you have to connect x and the y together. And you already got the, you always got the third equation, which is going to be your constraint. Okay, now solve this equation for x and the y. You mean use substitution method or just, addition method? It depends on the nature of the problem. So what I'm going to do is I'm going to put the Replace the x squared here, or I can subtract it, doesn't matter. So I use the kind of a substitution method, continue here. So I put the x squared, so that can be 4y squared plus 4y squared equal to the 16. So that gave me 8y squared equal to the 16. So y squared is equal to the 2. And the y would be positive, negative radical 2. You see, that would end up in the y. Any question? Remember, you are looking for the x and the y. Now that I have y equal to the positive radical 2, I put it over here, one of this equation, and find the x. Okay. So this is it. I continue. I bring it back here or on the top, doesn't matter. So I have the y equal to the positive negative radical 2. One of them just would be fine. So I put it inside here. So that give me x squared equal to the 4 times radical 2 squared. So that give you 4 times 2, which is equal to the 8. So that give you x squared equal to the 8. So I take the square root. X would be positive negative radical 8, which is 2 radical 2. Positive negative 2 radical. Don't use calculator, just give us these numbers. So this is it. So what we have, the solutions are going to be, the possibilities are going to be positive negative 2 radical 2. And this is going to be y equal to positive negative radical 2. Okay, so these are all the possible values for that point that eventually going to be your your critical points. So put them together, form critical points. So the points are going to be, so these are going to be possible critical values, critical points. Okay, critical points are going to be, just make 4 points. So one possibility is 2 radical 2 and radical 2. The other possibility is 2 radical 2 and negative radical 2. The other possibility is negative 2 radical 2 and radical 2. And we get negative 2 radical 2 and the negative radical 2. These are going to be 4 possibilities for your critical points. You have to drop them back into the function and compare them together. The largest one is the maximum, the smallest one is the minimum. We find the absolute max and absolute min in this case. Again, if you go with the linear, we call it linear programming in college algebra. You graph this, and these are the corners, they call it over there. You get a corner of the intersection of those graphs, and then you drop it back into the function to get the maximum and the minimum. Okay, so function, remember f of xy is going to be x times y. You have to substitute those 4 numbers and find out what is going to be the largest value and the smallest value of the function. Okay, so I'm going to go to function and get these numbers. Okay, already. Again, it's nice procedure, not difficult, but it takes times. It's not bad to know this beautiful method, really. Okay, so you have to drop them back into the function. Remember, your function is this. You want to maximize x times y. So the possibilities. So drop those critical numbers and you get them. So it's f of 2 radical 2 and radical 2 give you 2 radical 2 times radical 2. Radical 2 times radical 2 would be 2. 2 times 2, 4. So that would be 4. The other possibility was f of 2 radical 2 and negative radical 2. Okay, you know that give a negative 4. Negative 4, and the rest are going to be the same. If you put f of negative 2 radical 2 and radical 2, that give a negative 4. And the other possibility was negative 2 radical 2 and negative radical 2, that give a positive 4. So the minimum value of the function, remember the max and the mean are the values, not the points. So the minimum value of the function is going to be a -4. Okay, -4. And the maximum value of the function is going to be a +4. And that give you the result. And if you graph this with the calculator, that give you, that give you the idea really that, you see, almost, I just want to give an idea. If you just take that ellipsis, it's going to be -4 and 4 over here, and the top is, you can check it with your calculator. So this is going to be kind of ellipsis that you're going to have. And then you get those 4, you know that you have to find this is going to be happen at the intersection of those two graphs that we talk about it. So, roughly you may get, this is going to be one of the graph. You see, you get x, y equal to the 4. You know that y equal to y over 4 over x is a kind of a hyperbola. So roughly this is, kind. I think so. And you get a 2 here, probably. And you may get another one here. I'm not quite sure, but so this is what would happen. In the case of college algebra, they were all a straight line. In the region that you get in the college algebra, you shade it because you don't have the tools to find it. We call it a linear programming over there. But it's a quite interesting problem, and I told you there are softwares that you can do it to get these ideas. But it's nice to know Lagrange multiplier. Okay, so we stay with the 2 variables. Okay, if you have a function of 3 variables, you've got to be patient to find it. We are not going to give you that, but I write it down for you in case you want to know it. That because if you have a function of 3 variables, you should be given 2 constraints. So you have, instead of the function g or the vector g, you're going to have g and something else. Because when it's a 3x, y, z, then it's a 3 variable by itself that you have the lambda, so you need more equation to be able, to take care of it. So I just write it down, but I'm not going to question you on this one. It's good to know it in case you are interested in this type of ideas. But the one that you see on the test is of this group, okay? Just ellipsis. It's a straightforward. We have no difficulty to get this one, okay? So just to remind you for your record, this is function of 3 variables. We call it optimization, if you like. Optimizing, if you like. Optimizing a function with 2 constraints, a function. Some people are interested with 2 constraints. So your function is a function of 3 variables, and you need 2 conditions to do it. It's going to be the same thing, the idea. So we can extend, or one can extend. Okay, one can extend the idea, the method. Okay, the method of Lagrange multiplier. Okay, Lagrange multiplier. To a function. To a function of 3 variables. Okay, 3 variables. So your function this time is going to be f of x, y, z, but subject to 2 constraints, of course. Subject to 2 constraints. Okay, your constraints are going to be g of x, y, z equal to the 0 is one of them. The other one, they go with the h of x, y, z equal to the 0. So in that set of one scalar, in this case, we're going to have two scalars. And you put those arguments together. So again, you assume that, you see, the point that we're going to find should satisfy all these conditions. So assume that these surfaces, if you like, that we consider have a intersect point, they intersect in a curve. Okay, in a curve, and try to find the extremum of the function of f on the curve. So we should solve, okay, that's it. So one should solve this equation. Solve the following system. System with this one, you see gradient of the f at the point x0, y0, z0 is equal to the lambda, as we did it before. The function, the gradient of the g at x0, y0, z0, plus you need another scalar. We call it mu. The gradient of the h at x0, y0, z0. Okay, you need two multiplier where lambda and mu are going to be Lagrange. Okay, Lagrange multipliers. So that's, you know, if you wanted three, but it takes times to find it. Okay, when you put them together, you have a number of the equations and you have to go through these. Okay, if you are interested in, you can have a look, but otherwise it can be done with different, you know, numerical methods in future. So we are done with the chapter 13, and we're done with the first part of the course, really, which is the derivative of a function of several variables. So for the rest of the course, up to the final, we stay with the integrals, which is quite interesting. Okay, so I just list the topic that you have to learn. Okay, you have to know for the test. 5 questions from the quiz. You just check those. We have a continuously listed so that you are going to be okay. Any question? So the topics for the test, that's it. Topics for test 2. That's it. You can bring one page, two-sided, any formula you need. Okay, I checked the formula last time. It was all right. So just do the same thing. And make sure you bring a correct formula. Okay, so the one from your quiz, those 5 questions are going to be, the first one was as we did it. You should be able to find the domain. Okay, domain, range, and graph. Just describing the graph, not graphing. Graph of a function of several variables of the function. Okay, function of 2 variables. That was the one like the one you did on the, you know, on the quiz. That's the first one. The second one is the limit. The limit of functions. So, you know, we just give you one ordinary one, you know, a straightforward one. These are ordinary one that you did. You don't need anything special. Okay. Then this is going to be the limit again but I would like you to be able to prove that the limit does not exist. Remember those techniques that you have to use, different directions, x-axis, y-axis, etc. So number 4 is continuity. One question on continuity of functions. Again, remember the piecewise defined function or just a straightforward one. So you are going to check this for us. So that is going to be the one. Number 5, partial derivatives. Partial derivatives. Again, as you did it on the quiz. Then the 6th one is going to be linear approximation, linearization, linear approximation. Those ideal and estimated. Make sure you're able to find the LX, LX, Y, or sometimes LX, Y, Z, and then get estimate. So make sure you get the formula available. Okay. So that's the 6th one, and the 7th one, the chain rule, of course. You have one question on chain rule. You have something easy to evaluate for us. Okay, chain rule. That's a number 7. And number 8, directional derivative. Directional derivatives. We give one function and we ask you to find the derivative. Make sure your formula is available. Okay. This is going to be a directional derivative. You may get 2 on directional derivative because of that optimization problem that we have. Okay, just make sure you get it right. So the number 9 is going to be the one that we did today. Okay, relative extrema. Relative extrema, second derivative test. Just make sure you have the D formula, everything is ready. And number 10 is going to be Lagrange multiplier. Lagrange, okay, multipliers. So it would be 11, you may get 2 on the directional derivative because we have the optimization problem, remember, regarding this case. So mostly I haven't missed anything. No, these are going to be all you need to know really. Okay, the main concept. So just to study that, you shouldn't miss it. You'll be able, you're able to do it right away. In a case of this optimization problem, you may leave you to pick those points for us. Just be careful. So you pick something, something nice. So I'm going to do. You have all these, on your practice one, but I just check one of them to show you that the video maybe ask for it, and you should be prepared yourself to find it. Okay, because sometimes the people questions. Okay, any question? So you get the topics. Make sure your formulas, especially for the second group, your formulas are ready, and no surprise. Okay, 2 hours and 30 minutes. If you want to make an appointment, 2 hours and 30 minutes and 11 questions, and you are going to answer 10 questions from these topics. The first group, your quiz, and the second group, 1 from each that we talk about it today. Okay, the one that we did today are not going to be difficult. Okay, and just put them together. Okay, that optimization, because I'm not you see, you are going to be an APC, so I'm just to describe this problem the way you should know it. Okay, so this is from practice. We have the solution of all of them. I just explained this one to make sure that we have not going to have any to be confused. Okay, this is problem number 2 on your practice one, linearization. In this problem, I just changed the expression, the way we are going to, let me just bring it for myself. And then I tell you what it is, this one. Yes, this is problem number 2. See, this is the way we like it. So we'd like you to find, okay, this is it. Would like you to apply. This is the way we change it. Apply. Okay, apply the linear approximation or the linearization. Linearization of this function of f of x comma y equal to the square root of 9 minus x squared minus 2y squared, okay, to estimate the value of f of negative 0.91, and this is going to be 0.82. You see, in the test, they ask you to find the linearization at the point. You see, at the point -1 and 1, then estimate. We don't usually give you the point. So we'd like you to guess the point yourself. Okay, so it's going to be your job. Don't be confused when you see it. So when this is given to you, you realize that you need a point to estimate it. You look at the given numbers. So you are going to pick a number that's going to be close to this one, and it should be nice. Nice means it must be a perfect square. So try it for yourself. It must be maybe a function of 3 variables. So in this case, it's clear that this is going to be close to the -1, and this is going to be close to 1. But you quickly substitute here to make sure that it's going to be a perfect square. You see, because otherwise, if it's not going to be perfect square, so we don't want to start using calculator right at the beginning. Okay, yes, round it up to guess what is going to be your numbers. Okay, so you realize it, that because you need a perfect square. You need a perfect square, usually it's true. So do it yourself rather than the point would be given to you. So you realize that the point of estimation for this problem, okay, so you realize that the point of estimation for this problem is you run this one to the -1, and this one is going to be just 1. Okay, so if you find the linearization at this point, then you can say that. You see, then you can say that the f of x comma y is going to be the same as L of x comma y when x comma y is going to be approximately -1 and 1. And then you have the license, see, to substitute it. So just pick the nice number, which is going to be a perfect square. So we can try it to find out that the f of -1 and 1 in this case is going to be 9 minus -1 squared minus 2 times 1 squared. So that gave you 9 minus 1 minus, okay, 9 minus, oh, this is not going to be perfect, so it doesn't matter. I have to change it a little bit. So the one that you're going to see is going to be a nice one. So it's going to be radical 6, but the number is close. Okay, we usually give you something which is going to be nice. But you have to pick that number yourself. Okay, and you know the rest. We just find the L of x comma y is going to be, make sure you get the correct formula, f of -1, 1 plus the partial derivative of x times it by x minus -1, which is a positive one, okay, plus f sub y, and this is going to be y minus 1. Make sure this formula is correct. I don't know why. And, on the test that we have done it, for several times, some people, they use negative here. It's not, it's positive. Okay, make sure your numbers, your formula is correct when you bring it back. Okay, then you just go and find this. You already got f of -1, 1. Carefully find the partial derivatives. Okay, so there you are. You rewrite your function as the 9 minus x squared minus 2y squared to the 1/2, differentiate it and find it at 1, 1. So we're just using the chain rule. So this is it. It's going to be 1/2 times 9 minus x squared minus 2y squared to the negative 1/2 times the u prime derivative with respect to the x. That gives us a negative 2x. So the 2 would be simplified. So you change it to the radical form. So that gives a negative x, and that's going to be radical 9 minus x squared minus 2y squared. Okay, you quickly find it at the point P, which is a negative 1, 1. So you substitute is going to be negative times a negative 1. And the bottom one is radical 6. So that gives 1 over radical 6. Okay, you don't have to rationalize it. Just keep it, because at the end, use your calculator to get the result. Okay, so we do the same thing for the f sub y. So the f sub y would be very much similar. And so that gives you 1/2 9 minus x squared minus 2y squared to the negative 1/2, and the derivative with respect to the y would be negative 2y. So in this case, you are going to get a negative. Okay, so that was a 4y, yes? 2 times 2, 4. So it's a 4y. Okay, so we simplified one of these, so that gives you 2y over the radical 9 minus x squared minus 2y squared. And then you substitute. So this is a 1 and negative 1. So if you substitute, that gives you negative 2 times 1 over radical 6. So the result would be negative 2 radical 6. Okay, so that's going to be f sub. So you quickly be able to find your linearization. So f of x comma y. Okay, it's going to be radical 6. The value of the function is the radical 6. Okay, then plus f sub x, which is 1 over radical 6. Okay, x plus 1 minus 2 over radical 6 times y minus 1. You don't have to simplify it because you're just interested in the estimate. Okay. Then you estimate it. You know that f of x comma y is going to be the same as L of x comma y when your point is close to negative 1 and 1. So the point that we are interested in is going to be what? The point is, now bring those numbers, negative 0.91 and 0.82. Okay, you substitute your calculator to get the result. So it's going to be radical 6, okay, plus 1 over radical 6. So the difference are going to be negative 0.91 plus 1 minus 2 radical 6. And this is going to be 0.82 minus 1. Okay, depends how do you want to simplify it. So this is going to be a radical 6 plus 1 over radical 6, but use your calculator to get the result. But this is what I have. I just subtract it, give you the result. Okay, 2 over radical 6, and that give me negative 0.18. Okay, then use your calculator to get the final answer. You can do the algebra if you like, find the common denominator. This is the way I did it, but you can use your calculator. If you want to stay with the algebra, this is going to be 0.09 radical 6, and this is going to be plus 0.36 over radical 6. Okay, then you add them together. This is it, 0.45 over radical 6. But eventually, the calculator result is 2.63. Okay, so you claim that the number that you got is going to be 2.63, but you're not done. You have to change it, check it with your calculator, and show us that you did that, okay? So with the calculator, Okay, just give us the number, don't simplify it and use it, drop it into your calculator. So dropping into the calculator means directly go and find it, f of negative 0.91 and the 0.82. If you substitute it directly, this means you are going to have a 9 minus negative 0.91 squared, okay, minus 2 times 0.82 squared. If you use your calculator, I have 2.612, okay? Just give us a number exactly that you get from your calculator to show that you did test it, okay? We need that last part. That would be good for you because you check it, okay? And that will give you the idea that you're not going to check it. Ask for 8A on the practice one. Let's see what's 8A. Okay, so that is something, the way they are going to express it. Okay, I do the problem 8A. Oh yeah, I forgot one of those numbers that I miss is tangent line plane. I give you 10 topics. That's a tangent line plane. Okay, good point. I'm do the 8.1 for you. Yes, I do it. Okay, so add, yeah, I add. I thought that was 11. Okay, this is it. Let me add it to here. Then I do it. Number 11. Okay, number 11 is going to be, that's section 13.7, tangent plane equation. Okay, of tangent plane. Tangent planes. That's a very good one, surfaces. We have two cases and we have it, and I do number 8 to explain it. Okay, so yes, it's a good one to explain for you because there are two cases. Okay, so be prepared for, don't be confused. You have to guess what's the number yourself. It's easy to guess, but I just want to make sure that you know that there's nothing, missing on it. Okay, I do number 8, which is new. Okay, tangent plane. Tangent planes. You want to write the equation of tangent planes. Okay, let me just bring it here to see what we have, 8A. So the 8A, you want to find the equation of a tangent plane. This is it. So find the equation, okay, of the tangent plane. Tangent plane and the normal line. All of them are going to be asked at the same time. Normal line, okay, to the graph, to the surfaces, if you like. So in part A, this is it. In part A, the function is z equal to the, okay, y, e to the 2xy at the point 0, 2, 2. You see, this problem would have two different versions, and you may give in both of them or just one of them. One version is that the equation is explicitly given to you, x equal to. That's an easy one. The other version is going to be surface level. Surface level means the equation is implicitly like the ellipsoid. If you have the ellipsoid, z is not given to you. It's mixed together. Okay, so the situation are going to be different. This is going to be kind of a 2 variables, the other going to be 3 variables. Make sure you know the difference. If this is going to be the case, the equation of a tangent plane is going to be, you see solution. The equation of the tangent plane is z minus z naught. It's like the linear approximation. Okay, and this is going to be f sub x times x minus x0. Okay, plus f sub y times y minus y0. Okay, This is like, you know, if you move the z naught to the other side, it's exactly the linear approximation that you're going to have. Okay, if you like, you know, we can move this one to the other side and call it, and you see, if you like, this is it. You see, this is going to be, your z naught is going to be f of x0, y0, and this is going to be f sub x minus x0 plus f sub y times y minus y0. If the z is given to you as directly, explicitly, this is all going to do it. Okay, the point is 0, 2, 2. Okay, so that would be your z naught if you like. So just go for it to get these numbers. Okay, if you go with these points, you see, if you stay with the top one, your x0, y0, z0 is 0, 2, 2. You see, this is going to be a situation that that you're going to have. So your x0 is 0. Okay, so x0 is 0, the y0 is 2, and the z0 is 2. Okay, go and find it. So what you do, you have to find the partials. Okay, so what's going to be f sub x? F sub x, this is the function. Just remind you that your function is y e to the 2xy. Partial derivative with respect to the x. The first one, no x here, so it's going to be y. So it's going to be y. Exponential function never change, but you have to multiply by u prime. U prime derivative of the top respect to the x. Derivative of the x respect to the x would be 2y. 2y. So you get 2y squared e to the xy. Okay. Find that at this point, 0, 2. So f of x at 0, 2 is going to be equal to what? That's it. Y is equal to 2. So 2 times 2 is squared. E to the x is 0. E to the 0. And so that give you 2 times 4 times 1, which is 8. So this is going to be f sub x equal to the 8. Any question? And so that would be the partial derivative. You do it the same thing for the f sub y. F sub y. Differentiate. This is your function. Since you differentiate with respect to the y and both of them contains the y, so you have to do it the product rule. Derivative of the first times second, second first. Derivative of the first 1 times second e to the 2xy plus second first respect to the y. Exponential function never changed. Respect to the y, derivative would be 2x times first, which is y. Okay. But you want it at what? At 0, 2. 0, 2 is equal to, if you put x equal to 0, that gives e to the 0. And this would be e to the 0. There is an x here, so make it to the 0. So it's going to be 1 plus 0, which is 1. So the partial derivative would be 1. Okay, question? So now we are almost ready to go back and give you the, okay, give you whatever version, the first or the second one, to give you the equation. Okay, so write the equation. And so there you are, z minus z naught is 2, so z minus 2 equal to the f sub x 8 times x minus x0, x0 is 2, is 0, plus f sub y, which is 1. Okay, 1 times y minus y0, which is 2. That's it. So that gives you z minus 2 equal to the, okay, this is simply 8x, and this is going to be y minus 2. Okay, you know that we usually move everything to one side. This 2 would be out. So it's an equation of the plane. This is the way we write it down. Z minus 8x minus y equal to the 0. So this is going to be the equation of the tangent plane. Tangent tangent plane. Done. Any question? Now normal line. Remember, you need the normal vector. The normal vector, we talk about it, is gradient. So to get the normal vector, it's a symmetric equation that we use, okay? So I put it over here for you, so you can see it. Normal line. Normal line. For the normal line, you need a normal vector. Remember, normal vector is gradient. In this case, f sub x sub y. And then you need a point. Point is 0, 2. 0, 2. So the partials, you already got them. F sub x is equal to the 8 and fy is y. So the partial are going to be 8, 1. Okay, and the point is 0, 2. Equation, it's a two-dimensional only. You see it's going to be x minus x0. Okay, x0 is 0, so it's going to be x minus 0, sorry. It's going to be x minus 0 divided by a, which is 8, is equal to the y minus y0, which is 2, divided by 1. So that's it, to get an x over 8 equal to the y minus 2. So y equal to the 1/8 of x plus 2. It's the equation of the normal line. Nice. This is case 1 of this type of problems. Any question? So don't be confused. This is the case that the C is explicitly given to. There's going to be a case 2. The case 2 is when this equation is going to be implicitly defined. In that case, you have to a case, we call it okay, we call it surface level. It's the same thing. We already got give you the formula, so you have to know them. Okay, already let's just make sure give you the second case too. Z equal to, but the second case is not going to be Z, it's going to be kind of ellipsoid, circle, not circle. Okay, you can have a sphere. So the case 2 is this one. You want to find the tangent plane to this surface. X squared plus y squared plus z squared equal to the 9. At the point, what is the point? 1, 2, 2. Three-dimensional case. We say you cannot find the z, or we are not going to find it. But this version, it's the same thing. So what is going to be the formula for this? Remember the way we do it, solution. You are going to, you can move the 9 to the other side, introduce a function, surface level we call it. So you are going to introduce the function f of x, y, z to be equal to the x squared plus y squared plus z squared equal to the minus 9. Remember, that's the surface level. So to get a tangent plane to this one, tangent plane, the formula, if you want to check it with your lecture note, tangent plane to the level surface or surface level, surface, check this one and you can bring it. So that's your formula. It's the same thing. It's f sub x, the partial derivatives, at the point x0, y0, z0, okay, times x minus x0, plus f sub y, partial derivative, x0, y0, z0, times y minus y0, plus f sub z, at the point x0, y0, z0, times z minus z0 equal to the 0. Remember, in this case, if you like, the normal vector to your plane is this. You say this is going to be your normal vector. And your point is going to be x0, y0, c0. That's the idea. Okay, the only difference is, this is a surface level. Okay, so just find those quantities and go back and write it down. So you must know the format of these two. So let's do it. F sub x is the derivative with respect to the x, 2x. F sub y, 2y. F sub z, 2z. That's it. Evaluate at the point. F sub x point, what's point? 1, 2, 2. You just need the x. So that give it 2 times 1, which is 2. That's f sub x. Okay, continue f sub y. 1, 2, 2. It's a 2y. Y is 2. 2 times 2, 4. Okay, fz. Z. 1, 2, 2. It's a 2z. Z is 2. 2 times 2, 4. That's it. This is your normal vector. Okay, let's go normal vector. And the point is x0, y0, z0 is 1, 2, 2. So write the equation. Okay. That's it, partial 2. X minus x0, 1. Plus fy, 4. Times y minus y0, 2. Okay, plus f sub z, 4. Z minus 2 equal to the 0. And you have to simplify it, remember. So it's going to be 2x minus 2 plus 4y minus 8. And that's a 4z minus 8 equal to the 0. So that's going to be a 2x, okay, plus 4y plus 4z. The numbers negative 16 and minus 18 equal to the 0. All of them are divisible by 2. So that gives x plus 2y plus 2z minus 9 equal to the 0. This is going to be the equation of a tangent plane. Okay, that gives a tangent plane equation. Any question? So just, make sure you know the idea and the difference between two cases. Of course, they ask for the normal line. The line that's going to be perpendicular to the tangent plane. So normal line. You know that this is the line. The normal vector is going to be gradient. Okay, again, n is the gradient, f sub x, f sub y, f sub z, and you already got these numbers. 2, 4, 4. 2, 4, 4. And the point is, let's point 1, 2, 2. Symmetric equation. Remember, symmetric equation. X minus x0 is going to be x minus x0 minus 1 divided by a, which is 2. Y minus y0, which is 2, divided by b, which is 4. And the z minus 2 divided by c, which is 4. So this is going to be the equation, symmetric equation of the normal line. Okay, just make sure you are not going to be confused between these two cases that we are going to have for number 8. Okay, I think that's it. You can check the other solutions from the practice one. You have all the solutions over there. So read it carefully. It's, you get lots of formulas, but it's not bad. It takes times. So make sure you practice, make sure that all your tools are available. But you should be able to do it in that 2 hours and 30 minutes that we have. Okay, so I check your quiz. I will finish it and I post this. Your quiz, just check it, make sure that you are not going to make a mistake, because the similar one would be given to you. And the argument that just check those relative extremum that we have. It's number, number 10. Check those equations. Make sure you're happy about it. That system of the equation, your partial x equal to 0, y equal to 0. And just make sure you are, you're not going to be happy when you want to solve that system of two variables. And that's it. Any question? So check all those and let me know if you have any question. So the test, you can take it on Monday, Tuesday, and Wednesday, but we are going to have a class. Even if you miss it, make sure that you read or check the recording right on the day, okay? When you come every day next week, make sure you know what we are going to be talking about, especially the first part of the integration is not difficult, but important to make sure you don't miss anything really. Otherwise, you'll be fine. You're doing fine. Okay, have a good one and let me know if you need anything. Okay, good luck. Thank you. Bye-bye. I'll post the recording and this lecture notes for you. Bye-bye.